To all of you joining me for this video, thank you. I am Mr. Ish. I hope you're all having a great evening. We're looking here at a calculus application, the probability density function, which is basically the application of calculus for probability determinations. But before we do that, we need to look at this concept of a continuous random variable. Hypothetically, if you were to take a random individual, a person, from a group of individuals who were probably categorized by whatever means, sex, age group, any other number of categories, and you select this individual, you take out a blood sample and you start measuring the blood glucose. I'm just abbreviating it, blood glucose, BG. You know, when you're looking at a blood glucose, it actually has a numerical value, like a number pops up. And that number, for all practical purposes, can be anything from perhaps 0 up to 1000. 0 meaning like there's no glucose in the blood, 1000 meaning an artificially high value. Technically, if you're looking at some sort of sample, it could really go from minus infinity to infinity. But in the realm of practicality, we're looking at from 0 to 1000. But we know in terms of healthy blood glucose levels, we're looking at something from 75 to 110. That represents a normal value. You can look at this right here, continuous random variable, exactly with regards to what I'm saying. This right here is a type of a variable which can be represented within a range of variables, like a range of real values from one interval limit to another, and your random variable would fall somewhere in between. That exactly is a continuous random variable. It could have taken any value, any real number value or integer value from one limit to the other. You can use probability density functions to represent all of this graphically. If you're looking at a distribution curve, something which would look like this, you know you'd be looking at something here with regards to your x-axis, your y-axis, very likely the probability over here, and exactly the sample value over here. If you're looking at everything here from 0 to 1000, we can do 0 to 1000. But if you're looking at everything from here to here, 75 to 100, you'd be looking at something from here to right over here. The area below this would be very representative of the probability that you're randomly selecting an individual from a group, and the probability that his or her blood glucose level would be in this level, in between this range over here, would be represented by this area, the area below the curve. You can represent it such as a 75 to 110, whatever this function equation is. You'd integrate it, and your numerical value of this definite integral would be representative of your probability of that occurring. X over here is your continuous random variable. That right there is exactly what we're talking about right here. But you can do a little bit more than this. Represent this as you're seeing, such as is the probability that your random variable fell between this range right here. Let me make this 110 because we're talking about 110 and 75. But you can also determine, utilizing the same model function f of x, what's the probability that this person's blood glucose level is now larger than 110, or what's the probability that the person's blood glucose is less than 75, hypoglycemia or hyperglycemia. All of these things you can check utilizing calculus with regards to this probability density function. The area below the curve is very well representative of the probability of that variable with regards to the event or the likelihood of that event occurring. These probability density functions are very well indicative of what I'm showing you here. You just have to understand continuous random variables are those variables which can adopt any value from a range of values. Any of those values would be very well within the scope of that likelihood occurring. You know, probabilities are always measured from 0 to 1. This would be 0%, the likelihood, there's no chance that the event is occurring, to 100%, that 100% of the time that event is occurring. Most probabilities fall right here in between, a value usually larger than 0 or less than 1. That's generally the norm. The probabilities fall over there. Very generally, the probability density function satisfies the condition that f of x, right here, your function, is always greater than or equal to 0 for all values that are being investigated, for all x-axis values. You can also very well represent from minus infinity to infinity f of x, that if you were to do this integral, you'd always have a value here of 1. If you were to determine that and always achieve a value of 1, then that function you're looking at indeed is a probability density function. I want to present a single example. It's just a hypothetical example. I've taken it out from a calculus book, and I'll give the credit in the video information section, and we'll just evaluate that from start to finish. and that will give us an idea of how this probability density function and this integral calculus plays into all of this. So the function we look at is this right here. The question we look at is this, and I'll give the credit in my information for this video. If function f of x is equal to 3 divided by 64x root 16 minus x squared, that right there is the function. For this right here, 0 is less than or equal to x, which is less than or equal to 4. This probably represents some probability event, the likelihood of some event occurring, or what the event is. And these are basically your continuous random variables, the range of those continuous random variables. And your function is f of x is equal to 0 for all other x values. We have to verify the function is indeed PDF, probability density function, and we have to find the probability this x is less than 2 right here. It's less than 2. Let's look at exactly what this is saying. Imagine if the function looks like this, a normal curve like this. This right here is my function. I'm not saying that's the graph of it, but imagine it looks like this. Look at it. Less than or equal to x, which is less than 4. We're calling this 0 and we're calling this 4. 0 to 4. But look right here, and f of x is equal to 0 for all other x values. What is f of x is equal to 0? That's y equals 0. What is that? Your x-axis. Then it's just the x-axis. We're looking at that. We have to verify that this function f of x is a probability density function. Don't get confused by this extra language. It's just showing that the rest of the function is basically very well your x-axis, y equals 0. How can you verify that this function is a probability density function? Well, you have to integrate this from the interval you're looking at. Basically, you're looking at something which looks like this, minus infinity to infinity, f of x here dx would be like this, 0 to 4 f of x dx, because the rest of the values are equal to just your x-axis, y equals 0 for all other x-axis values. We just have to show you this right here is equal to 1. If this right here is equal to 1, we do have a probability density function. So let's show you that to be the case. I'll erase it and make some space. You have this from 0 to 4, you have a 3 over 64 sitting outside. You have x root 16 minus x squared dx. Use polynomial substitution. U is equal to 16 minus x squared. Du is equal to minus 2x dx. Dx is equal to du over minus 2x. Come up with your new intervals, u1 and u2 with regards to this. 16 minus 0 square, well, it's a 16. 16 minus 4 square, well, that's a 0. You have a 3 over 64. You have here now a 16 and a 0. You have an x, you have a u, and then a du over minus 2x. See, minus 2x. I'm bringing this minus 1 over 2 out. Nothing wrong with you doing that. Minus 1 over 2 has been brought out. This 2 has been erased. These x's cancel out. The minus has already been brought out over here. You see that. I'm going to simplify this. I have a minus 3 over 128. Let's write that. Minus 3 over 128. But I don't like the appearance of those intervals at all. I want the bigger number back here, so I can do that, and I can flip the intervals around, but I need to bring a minus to do that flip. I want to convert this into an exponential form, which I will, u to the 1 over 2. When I integrate this, I have a 3 over 128. I have a u to the 3 over 2 over 3 over 2. This 3 over 2 really becomes a 2 over 3 when you flip the fraction around, and I'm doing that. I'm looking at everything here from a 16 and a 0. These 3's cancel out. I have a 2 over 128, which is a 1 over 64, times 16 to the power of 3 over 2 minus 0 to the power of 3 over 2. 16 to the power of 3 over 2 is really a 64. I see a 64 over 64, which is equal to 1. So this entire function here from 0 to 4 actually equals a 1. So I am indeed dealing with a probability density function. And because I can do these probability evaluations and determinations. So the question part A has been done. I've shown you how we can get the 1, and it's done. Now let's look at part B. We have to determine the probability the x value was less than 2. We have to determine now this probability of x is less than 2. How can we do that? The function is still the same. You're looking at 3 over 64, but now you're looking from 0 to 2. If this right here were your graph, from 0 to 4, right over here, we're now looking from 0 to 2. We're now looking at this area right over here, area below the curve. The area below this curve right here will represent the probability of that right there. But nothing is drawn to scale, but we'll still calculate it. You've seen this. We have this x root 16 minus x squared dx. Let's do the polynomial substitution. U is equal to 16 minus x squared. Du is equal to minus 2x dx. and dx is equal to du divided by minus 2x, u1 and u2. With regards to this, u1 is equal to 16 minus 0, well that's a 16. u2 is equal to 16 minus 4, which is a 12. So what am I seeing over here? I'm seeing a 3 over 64, I'm seeing a 16 and a 12. I have an x, I have a u to the 1 over 2, which is my root u, I have a du divided by minus 2x. But I want to clean all of this up because I need space. I'm going to bring this minus 1 over 2 out right over here, and I've done that. I'm going to cancel out the x's, so I might as well just erase them, and I'm doing that. I have a minus 1 over 2, 3 over 64, and all of that. This minus 1 over 2, 3 and 64 cancels out and becomes a minus 3 over 128. I don't like these intervals. I want to flip them back around, and I'm going to flip them back around by bringing in a minus. I can bring in a minus, but when I bring in the minus, these negatives cancel out. I might as well just cancel them out right here and make it 3 over 128, and that's what I have. Now let's integrate that. I have 3 over 128. I have u to the 3 over 2 over 3 over 2 from an upper limit 16 and lower limit 12. This 3 over 2 can flip around. You have a 2 over 3. We can erase this. I apologize for all of this erasing I'm doing, but you know all the procedures. 2 divided by 128 is really a 1 over 64, and let's do that. 1 divided by 64. We really have now 1 over 64 times 16 to the power of 3 over 2 minus 12 to the power of 3 over 2. This right here will give us the probability of this event occurring. We don't know what this model represents or what this event is, but we can at least determine the probability. We'll do 16 exponent 1.5 minus 12 exponent 1.5 divided by 64. I get a 0.35048. I'll just write this. 0.350. That's the probability of this event occurring is 0.350, or 35 out of 100. You see how we've determined this by means of the probability density function, and then utilizing integral calculus for whatever interval we have. Here our interval here is basically 0 to 2. That's what we're looking at. Here the interval was 0 to 4, representing the entire model. But you can always do piecemeal things. You could have done probability right here of 2 less than equal to x, which is less than or equal to 3, and this would give you a different probability for the same model. So you can do all of these probability determination so long as you have a good probability density function and everything is amenable to integral calculus procedures. And that's what I'm showing you in this video, and hopefully it's informative. Thank you for watching this video. You all have a good day. Bye.